Hello students, welcome to the lecture series of rotational dynamics. The topic that we are going to see today is relation between the torque and angular acceleration of the rigid rotating body. So basically what we are trying to do today is prove the relation tau is equal to I alpha. Tau is equal to I alpha, where tau is the torque, I is the moment of inertia, and alpha is the angular acceleration. So let's start with the proof of this considered relation. For that, we have drawn a diagram on the left hand side of the screen where I've shown a rotating body and some particles on the rotating body, M1, M2, so on up to Mn. The body is rotating about an axis, vertical axis as shown in the figure, and about that axis, the angular acceleration of the body is alpha. So the concept that we are going to use to calculate the torque acting on the rigid rotating body is basically we are going to find out the torque acting on each and every particle, and then we are going to do vector addition of all those torques. So basically tau body will be nothing but tau 1 plus tau 2 and so on up to tau n. So we are going to calculate the torque acting on each and every particle, and we are going to do the vector addition to find out the total torque acting on the rotating body. Now, we know that for any particle, the torque acting on that particle is R bar cross F bar. R bar cross F bar, where R bar is nothing but the position vector of the particle from the axis of rotation, and F bar is nothing but the force acting on the particle. So R bars we can already see in the figure. For mass M1, R bar will be R1 bar. For M2, it will be R2 bar. For Mn, it will be Rn bar. The question that remains is, how do we get F bar? Basically, what is this F bar? So the answer to that question is the F bar vector is nothing but tangential forces acting on all particles performing circular motion. And we know that these tangential forces are going to be perpendicular to the position vectors. So I draw the tangential vector for mass 1 like this and I write it as Ft1. For mass 2, I draw it like this and I write Ft2. And for mass n, I draw it like this and I write Ftn. So Ft1 is the tangential force acting on particle 1, Ft2 is tangential force acting on particle 2, and Ftn is nothing but tangential force acting on particle n. And they all are perpendicular to their respective position vectors. So when I am calculating the torque for any ith particle, Ti bar, it is nothing but Ri bar cross Fti bar, Ri bar cross Fti bar, and if I write down the magnitude, it will be just Ri into Fti, because sine 90 will be 1 as theta is equal to 90 degree. As theta is equal to 90 degrees, sine 90 will be 1. Now, it is very important to find out the direction of all the torques acting on all the particles. Now, if we consider any particle, let's consider particle 1 and draw the position vector and the tangential force vector, then they are like this. The position vector is like this, R1 bar, and the tangential force vector is like this, Ft1 bar. Now, to find out the direction of tau, that is the torque vector, we just rotate Ri bar in the direction of Fti bar, and we are observing this rotation from the top. So when Ri bar is rotated towards Fti bar, then we can see from the top that the rotation is anti-clockwise rotation, and whenever the anti-clockwise rotation exists, the direction of the cross product is towards us, which means that the direction of the cross product is upwards. The direction of the cross product is upwards, and therefore from this we can conclude that all TI are directed upwards. Directed upwards in direction of alpha bar. In direction of alpha bar. Okay, so we now have the magnitude of the torque acting on each particle, and we also know that the direction of the torques acting on all the particle is same, and it is nothing but vertically upwards. Okay, so this is the information that we have collected up till now. That is tau I, which is torque acting on any particle, is Ri into Fti, and the torques acting on all the particles are upwards. So let us try to simplify this formula further. So we have tau I is equal to Ri into Fti, where Fti is nothing but the tangential force. Tangential force. And this tangential force can be written as mass of the particle into tangential acceleration. So ATI is the tangential acceleration on ith particle. Now, we know that the tangential acceleration's vector formula is alpha bar cross r bar. So ATI bar will be alpha bar cross Ri bar. Now, if we see the figure once again, I'll just bring that figure again. Okay, so I've brought the figure, and we can see clearly from the figure that all the position vectors, that is r bar, are perpendicular to the vector alpha bar, because the vector alpha bar is going to be vertically upwards along the axis. All the r bars are in the horizontal plane, and the alpha bar is vertical upward along the axis. So alpha bar is going to be perpendicular to r bar, and therefore the magnitude of the tangential acceleration for any particle can be written as alpha into Ri. Alpha into Ri. We just require the magnitude because we already have decided the direction of the torques, that is vertically upward. So we do not need direction now. We just need the magnitude of the tangential acceleration. So let's take that magnitude of tangential acceleration and put in the place of ATI. So we have Ri, Mi, ATI can be written as alpha into Ri. So for ith particle, the torque, finally what we are getting is Mi Ri square into alpha. Mi Ri square into alpha. And as we have said that all the torques of the particles are in same direction, that is vertically upwards, their vector addition becomes simple. We just need to add their magnitudes as we add the scalars, and the result will be nothing but the torque acting on the whole rotating body. So torque acting on the whole rotating body is nothing but summation of I is equal to 1 to n Ti, which is nothing but summation of I is equal to 1 to n Mi Ri square alpha. Mi Ri square alpha. Now let's substitute the values and see what we are getting. For the first particle, we have m1 r1 square alpha. For second particle, we have m2 r2 square alpha, and so on up to for nth particle, we have mn rn square into alpha. And if we common out alpha, what we are getting is m1 r1 square plus m2 r2 square, so on up to mn rn square whole multiplied by alpha. And as we have been doing since the last derivation, this bracketed term looks like moment of inertia, and therefore in the place of that bracketed term we can write down moment of inertia of the body, which is nothing but I, and multiply it with alpha to get the torque acting on the rotating body. So the torque acting on the rotating body can be written as moment of inertia of the body times angular acceleration of the body. So thus we have proved that the torque acting on body is nothing but I into alpha. Now, if we want to write down the vector notation, we can easily write down that the tau bar, that is the torque acting on the body, is I times alpha bar, which means that the torque will be parallel to angular acceleration. Angular acceleration. Angular acceleration. Okay, so this is the relation that we have derived. Tau is equal to I alpha. Now, I'll just end the lecture with a small point, which is the proof of a principle called as principle of conservation of angular momentum using the formula that we have derived. So, let's study this principle of conservation of angular momentum. Principle of conservation of angular momentum. Now, let's see what is this principle trying to tell us first. Okay, so I've written the statement of the principle of conservation of angular momentum, and it states the following thing, that for a system, if the external torque acting on the system is 0, then the angular momentum of the system is conserved. Now, this is similar to the principle of conservation of linear momentum, where when F external was 0, then the momentum was conserved. The momentum, that is linear momentum, was conserved. Now, in rotational dynamics, we have if external torque is 0, then angular momentum is conserved. Angular momentum is conserved. Now, let's try to prove this. It's a two-line proof by using the above relation that we have derived. So, we know that tau bar is nothing but I into alpha bar. Now, alpha bar is nothing but d omega bar by dt. That is, angular acceleration is nothing but the rate of change of angular velocity. Now, if I take the I inside of the derivative, I get d by dt of I omega bar. And we know I omega bar is nothing but angular momentum. So, finally what we get is tau bar is equal to dl bar by dt. And if tau bar is equal to 0, that is external torque is 0, then the derivative of the angular momentum with respect to time is 0. And we know when the derivative is 0, the quantity which is being differentiated is constant. So L bar is constant, which means that when the external torque is 0, L bar is constant, meaning that the angular momentum is conserved. Angular momentum is conserved. So, when external torque is 0, we have constant angular momentum, and therefore we can write L1 bar is equal to L2 bar, or the angular momentum at some initial time must be equal to angular momentum at some final time. And therefore we can write down I1 omega 1 bar is equal to I2 omega 2 bar. Now, this is the relation which we must keep in mind while solving the numericals. And from where did we get this relation? It is nothing but the outcome of principle of conservation of angular momentum. Principle of conservation of angular momentum. So in today's lecture, we have covered the topic of torque acting on the rigid rotating body, whose formula can be written as I alpha, where I is the moment of inertia, alpha is the angular acceleration. And finally, we also saw the principle of conservation of angular momentum, which states that if the external torque acting on the body is 0, then the angular momentum of the system is conserved, which means the angular momentum for the system remains constant. Thank you very much.